Solving a distance, rate, time problem using a system of linear equations. An airplane travels 2,240 kilometers against the wind in 4 hours and 2,760 kilometers with the wind in the same amount of time. What is the rate of the plane in still air, and what is the rate of the wind? I'm actually going to use the letter W and draw an arrow to indicate the wind. I'm also going to do an arrow here to represent the speed of the plane in still air. So if this is with the wind, the airplane is being pushed. I guess I could draw an airplane at the end. Pardon my terrible pictures, but here's an airplane of some sort. There's my airplane. And so this airplane is going with the wind. And we can see that the speed of the wind is greater than 0. And we need a letter for that red arrow. Why don't we call that R, which is the rate of the plane in still air. We also know that W is more than 0, but less than what? Less than R. That's really important. Why don't we organize the given information in a chart? We need a couple of descriptors. So let's say with the wind and against the wind. The first column of my chart is usually representing distance. We could have distance. And what is the distance with the wind? 2,760 kilometers. Against the wind, 2,240 kilometers. The next part of my chart is actually rate. I use a capital R. And the last column of our chart is time, and I'll use a capital T. So distance equals rate times time. The rate with the wind, well, is indicated from our picture. It's actually R plus W, right? The plane is going faster. It still traveled 4 hours, either way, or both ways. Now against the wind, it's got to be slower. And how much slower? So against the wind, in some ways, it looks like you're doing something like this. The plane is going this way, and the wind is actually pulling the plane back. This time the plane is flying the other way. Once again, pardon my bad picture of a plane. Something like that. So in this case, how do we recognize these arrows? A simple way of recognizing these arrows is making sure that the bigger rate is subtracted by the smaller rate. So what we need to write here is R minus W. And now we're in good shape. We're ready to solve for R and W. We could number our equations. Equation 1 could be 2,760 is equal to R plus W times 4. And equation 2 could be 2,240 is equal to R minus W times 4. 60 is divisible by 4, and 2,240 is divisible by 4. So we could actually simplify these equations. We could divide the entire sides by 4. I'm going to write a little small and fit them in there. And we could simplify. So what are our new equations? Let's find out. Put 4 digits there. You could use a calculator or use some scratch paper. Before you know it, you realize you get 690 is equal to R plus W. The next equation simplifies to 560 is equal to R minus W. Now this is rather convenient. We could simply add the 2 equations vertically and we could solve for R. So we get 0, 5, 12 here, and that is now 2 times R. We could divide the entire sides by 2 because 2 is not 0. R is equal to, what is that? That looks like 625. Yeah, 625. We also need to find W. So how can we find W? Why don't we take this equation and solve for W? W is equal to 690 minus R. But R is what? 625. So W is equal to, what do we got there? 65? 65. Now we need some units here. So if the problem is given to you in words, you should answer it back in words. The rate of the plane in still air is 625 kilometers per hour. And the rate of the wind is 65 kilometers per hour, period. Obviously, I'm going to circle my summary, but in reality, math is about showing your procedures and communicating it to another person. So why don't we circle all your work as well? The picture gives you an idea of what's going on. Of course, you guys could draw better pictures than I can. And that's it.